Hey everybody, and we are back for section 9.3, the distribution of the sample mean and the central limit theorem. So in the last video, I talked about the distribution of the sample mean. So if you don't really remember what that was, go check that out. Rewatch the video as many times as you need to. So remember, I talked about, you can, find all these samples and then find the mean of each of those samples. So you have a list of all the sample means, and then we can pop that into a probability distribution. Well, we can also find the variance of the sample mean and the standard deviation of the sample mean. And here are the formulas. I'm going to rewrite them so you can see them just a little bit better. So the variance of the sample mean, so variance is always sigma squared. Well, then they have this x bar down here. We call this a subscript because we're finding the variance of the sample mean. And to calculate that, it's just the variance of the population, which we notate with just a regular old sigma squared, divided by n, which is the sample size. So up here, this is the population variance. And then n is the sample size. We can also find the standard deviation of the sample mean. So remember, variance and standard deviation are closely related. If we have the variance, to figure out standard deviation, we just take the square root. So essentially that's what we're doing here. Imagine taking the square root of both sides of this equation. When we do that, well, we get the standard deviation of the sample mean. Standard deviation is just the sigma, no squared. That is equal to the population standard deviation divided by the square root of n. So on top, we got the population standard deviation, and then on bottom, n still equals sample size. It's just we take a square root. All right, so that is how we can calculate the variance and standard deviation of the sample mean. And just a quick note, we refer to the standard deviation of the sample mean as the standard error of the mean. The standard deviation of the sample mean represents how far the sample mean is from the population mean. So if there's a difference, right? If standard deviation is equal to 0, that means we're at the mean, right? Standard deviation is a representation, it shows us how far something is from the mean. It's a measure of how far something is from the mean. So if we have, error is just, it's difference. What's the difference between the sample mean and the population mean? And you don't really need to focus on this. This was more of just for your information. The standard deviation of the sample mean is also referred to as the standard error. Okay, so the main part of what I want to talk about in this section is the central limit theorem. So just to read through it. If a sufficiently large random sample, so for example, n is greater than 30, and usually that's what we want. We want a sample size of bigger than 30, is drawn from a population with mean mu and standard deviation sigma, the distribution of the sample mean will have the following characteristics. Number 1, an approximately normal distribution. That is, the distribution of the sample mean will be approximately normal. And remember, that just means it's a bell curve. So all distributions of the sample mean, if we have a big enough sample size, will start to look normal. Number 2, the sample mean, so this mu of x bar, this is the mean of the sample means. Remember we talked about that in the last video. We had that list of sample means with that valve problem. And then if you take the mean of that, that's the mean of your sample means. The mean of your sample means is equal to the population mean. And I have it written out right here. The mean of the sample means equals the population mean, which is awesome. And we're going to be using that idea as we move forward. Last has to do with the standard deviation. Basically, just give this formula right here. The standard deviation of the sample mean is equal to the population standard deviation divided by the square root of n. And basically, I don't have this written out here, but I copied this directly from the book. The bigger sample size we get, the less variability we will have. And this is actually perfectly depicted in this picture right here. So we have 3 different sampling distributions here. The population standard deviation is 2,500. The population mean is 43,660. But over here, they have 3 different sample sizes. First, they have n is equal to 25, so it's a sample size of just 25. So they found all possible samples of size 25, and they found all the sample means. And then they built a probability distribution, and it looks like this. It's kind of flat. It's this bottom pink one, purple, burgundy. I don't know what color you want to call that. It's kind of flat. Okay, well, what happens if we up the sample size? So instead of 25 for sample size, let's look at 100. Well, we don't get as flat. We get a little bit taller, more bell-shaped, right? And as we kind of get skinnier here, this means that we are having less variability. You know, the spread from the mean is getting smaller, right? You know, points on this first curve, the burgundy curve, you know, they're spread out pretty nicely about the mean, but get a bigger sample size of 100 and they move in, right? And they get closer to the mean, which means less variability. And then last, they have one for 200, a big sample size of 200. Again, they found all possible samples of that size, took all the means of those samples, and made this distribution. And once again, it's even skinnier. So our values are getting closer to the mean, which again means less variability. So as sample size increases, variability decreases. There we go. That should say decreases. Anyway. So that is the central limit theorem. How are we going to be using this? We're going to be using this to solve problems. But before we do that, one last thing I want to show you. We'll be solving problems in the next probably 2 videos. Another thing I'm getting caught up in my words here. Let me slow down. So if we look back at number 1 in the central limit theorem, an approximately normal distribution. The distribution of the sample mean will have the following characteristics. And number 1 is an approximately normal distribution. So what that means is, no matter what the distribution of the original population looks like. So in these pictures, we have bimodal. That's this first one. We have exponential. We have normal. And we have uniform. These are all different types of distributions. Well, once we find that distribution of the sample mean for large samples, bigger than 30, look what happens. They all turn out normal. which is fantastic because in chapter 8, we talked about, finding probabilities for random variables and like what's the probability that a random variable is within a certain interval. And we're to be doing the same exact thing, but with sample means. What's the probability that a randomly chosen sample has a sample mean less than this value, or greater than this value, or between these two values, so on and so forth. All right. So that's my discussion, my intro into sample means and the central limit theorem. The next video or videos will be focused on solving the actual application problems that you will see in the homework. See you then.